All right, the topic that we're dealing with here is computing the osmotic pressure of a solution. So here it shows a cell, and it's surrounded by a solution. And just looking at the picture, how would you describe the solution surrounding that cell? Hypertonic. Hypertonic. It's got a higher proportion of solute particles relative to water. So the proportion of solute to water is higher here in the fluid surrounding the cell than inside the cell. All right, you can just look at it. And so which direction is water going to tend to flow or diffuse? Is it flowing in or flowing out? Diffusion is always where a chemical flows from higher to lower concentration. So where is the higher concentration of water? Inside the cell. Look, I drew boxes just to show you a relative area. Doesn't it look like there's more space for water here than here? No? Look, wherever you have more solute particles, you have proportionally less water. Wherever you have fewer solute particles, you have proportionally more water. Right? You have every solution is a combination of solute and water. So where there's more solute, there's obviously less space for water. So what's water going to do? It will flow out. And as water flows out, we call this osmosis. And what's going to happen to the cell? It'll undergo crenation. It'll shrivel up and collapse. All right, so that's not good. All right, now incidentally, when we say that this inside the cell is a higher proportion or higher concentration of water, I'm not claiming that there's more water in the cell than out here. I'm saying the concentration of water is higher. Concentration is the relative proportion of solute to water. Okay, if we totaled up the total amount of water out there, that might be more. But we're not talking about where there's more water, we're talking about the concentration or proportion of water. And there's a higher concentration inside the cell than out. Now, in the middle picture, what is it trying to show? It looks isotonic to me. Doesn't it look isotonic to you? Doesn't it look like the relatively same proportion or concentration of solute and water inside as outside? So that's isotonic. What's water going to do? There will be no net movement. Some water may flow in, some water may flow out, and there's no net tendency to go in either direction. All right, so the cell was happy. Okay, now I drew another cell here. I drew another cell, and in this case, I just put dots and representing solutes, most of which are proteins, and then the rest of it is water. And I even labeled that as is typical, it's 80% water on the inside of the cell, 20% other stuff, mostly proteins by weight. That's typically isotonic. Now, I depicted that surrounding the cell is 100% water. What would we call this fluid then surrounding the cell? Hypotonic. Very hypotonic. There's no solutes at all. So where is there a higher concentration of water? Outside or inside? Outside. Obviously outside. It's all water. So what's water going to do? It's going to flow in. And as water flows into the cell is going to start to swell up with water. And this flow of water into the cell, which is called osmosis, creates what's called an osmotic pressure. You ever heard that term? An osmotic pressure that's going to push against the cell membrane and eventually cause it to burst, to rupture. That's called lysis. Now we can actually calculate how strong this osmotic pressure is. And here's how we do it. We wrote right above here that for each milliosmol of solute particles difference between the inside and outside of the cell, it creates an osmotic pressure of 19.3 millimeters of mercury, or torr. Okay, so a couple of things to say. First, the way we commonly measure pressure in chemistry and in physiology and in medicine is in these funny units called millimeters of mercury. all of you who've had chemistry learned about expressing pressure in a chemistry course in millimeters of mercury, or they will also refer to that as torr nowadays. Anybody know why they call it torr? After Torricelli, an Italian chemist, all right? I won't test you on that. Not tortellini, though, that's something else. Tortellini is pasta. All right, so in his honor, they sometimes call it torr rather than millimeters of mercury. Now, if you've, whether you've had chemistry or not, I don't know if you've ever understood why they use that funny unit, millimeters of mercury. I am going to explain that unit at another time when we take up blood pressure, because blood pressure is also expressed in millimeters of mercury, or torr. Anyhow, this time we're expressing osmotic pressure in millimeters of mercury, or torr. So just to explain what this statement says, here inside the cell, since it's 80% water, 20% solute particles, that's isotonic, we have learned that isotonic fluids have about 300 milliosmoles of solute particles per liter. We talked about that last time. So inside the cell, the concentration of solute particles is 300 milliosmoles per liter. Outside the cell, it's 0. You'd say, how do you get 0? There's 0 solute particles. It's all water. There is no solute. So it's 0 milliosmoles per liter of solute particles. Remember, osmolarity is what? The total number of solute particles in a solution. That's how we defined it on previously, actually on, I guess it was page, when we talked about this, page, on page 9. That's when we first introduced the concept of milliosmoles. Anyhow, so we have just, this statement right up here says that for each milliosmol of solute particles difference between the inside and outside of the cell, it creates an osmotic pressure of 19.3 millimeters of mercury. Well, how many milliosmoles difference is there between the inside and outside of the cell? 300. 300 minus 0 is 300. So we can multiply 300 milliosmoles per liter, which is the difference in the number of milliosmoles between the inside and outside of the cell, times 19.3 millimeters of mercury per milliosmole. That means for each milliosmole of particles difference between the inside and outside of the cell, it creates an osmotic pressure of 19.3. As we multiply this out, the milliosmol units cancel out, and 300 times 19.3 is 5,790 millimeters of mercury. So that as the water flows into this cell, it creates an osmotic pressure that's going to actually burst that cell, and that osmotic pressure is 5,790 millimeters of mercury. That's amazing. That's really high. Incidentally, this is all written right down here for you. All right, so that's the size of this osmotic pressure. Now, with that in mind, I want to look at this chart that's immediately below. Now, again, okay, we're getting vibrations here. All right, now I prefaced my this whole presentation that I said be prepared, because the first 15 minutes or 20 minutes you're going to be scratching your head, and then I'm going to put this whole story together and show you why it's important. So just try to follow along. This chart basically describes the concentration of all these different chemicals in blood plasma, in tissue fluid, and in intracellular fluid. Now, you'll notice that the units that it's expressed in are milliosmoles per liter. Let me remind you of what we learned last class meeting. Remember the unit osmol or milliosmol is like the word fruit. So if we have, just like if I had 1 apple and 1 orange, I have 2 fruit. The idea of a milliosmol is that if we have 150 milliosmoles of sodium ions, let me say it again. If we have 150 millimoles of sodium ions, we have 150 milliosmoles of sodium. It's just like saying, so how many apples? Well, that's how many fruit you have. Why do we want to use that unit? we said that just the only way we can add apples to oranges is by calling them by a more generic word, fruit. The only way we can add millimoles of sodium ions to millimoles of potassium ions to millimoles of protein is to call them milliosmoles. So here we can see, just as an example, it indicates that the sodium ion concentration in blood plasma is 146 milliosmoles per liter. Does anybody remember what the number we told you to memorize for the normal sodium level in the extracellular fluids? About 150, and we had said milliequivalents per liter. Now, 150 milliequivalents of sodium, since it has a valence of 1, is 150 millimoles. And 150 millimoles is 150 milliosmoles. So really, whether we say 150 millimoles of sodium, or 150 milliequivalents of sodium, or 150 milliosmoles of sodium, it's the same number. Now the real number is 146. We asked you to memorize 150 is a nice ballpark number to keep in mind because certain electrolytes are very, very important. Anyhow, what I'd like to do is that first start by looking at the concentration of these chemicals inside the cell, intracellular fluid. So you'll notice that the amount of sodium inside cells is low. It's not 0. In fact, if you look back in our notes in the lecture outline, it was 15 milliequivalents per liter of sodium inside cells. We gave you 15. The real number is 14. It's close enough. But we're calling it milliosmoles, so we can add all these together. And you'll notice the potassium level inside the cell, we had learned the amount of potassium inside the cell is about 150 milliequivalents per liter, which is 150 millimoles per liter, which is 150 milliosmoles per liter. Because to convert from milliequivalents to millimoles, you just divide by a valence of 1, and 1 into anything is the same number. So it's all the same number. Yep.
But how can you just convert millimoles into moles so easily when a millimole is 1,000th of a mole?
No. I'm converting milliequivalents to millimoles.
Okay, and then millimoles...
These are the exact same questions we asked you to try on page 8. On page 8, you had to convert from millimoles to milliequivalents or milliequivalents to millimoles. You didn't change anything about multiplying or dividing by 1,000. All you did was either multiply times the valence or divide by the valence. And the valence of a potassium is 1. And in fact, we said, even if you can't remember to multiply or divide, whether you multiply by 1 or divide by 1, it's the same damn number. All right? That's all we're doing. So that's why these concepts, the math is really simple. There's nothing to it. But we have to understand these units because they throw these units around and they'll talk about milliequivalents or millimoles or milliosmoles and they assume you understand what they're talking about. All right, so make sure you go through this conceptually. All right, so you'll notice that this is inside cells. There's 0 amount of calcium, but there is magnesium. Way back on page C5 is where we told you which electrolytes, which chemicals were preponderantly found inside the cell and which ones were outside the cell. And we had mentioned back on C5, most of the magnesium is inside the cell, most of the calcium is outside the cell. And here we can see the amount of chloride and the amount of bicarbonate. There's not very much chloride or bicarbonate. And then it lists right after that, and I'll kind of enlarge it so you can see it. What the heck is this? On page 8, last class meeting, didn't I talk about monohydrogen phosphate? And why did I say it was important? It's the major buffer where? Inside cells. Anytime I ask these questions, it's rhetorical, I already know the answer. All right? I want to know if you know the answer, because I know exactly what I've covered. I've been doing this a long time. All right? So that's back on page 14. So it's simply indicating how much of that monohydrogen phosphate and also dihydrogen phosphate, that's how it's referred to, how much of these two buffers is inside the cell. And you can see there's a little bit outside, but a much higher amount inside the cell, and it's a buffer. All right, now what else is inside the cell? That's what we're focusing on. So it indicates the amount of sulfate, the amount of phosphocreatine, the number of milliosmoles of amino acids. Now remember, these are in milliosmoles. Milliosmoles is the same as millimoles. It just allows us to add all these different millimoles of chemicals together, right? It's just like one millimole of amino acids is 1 milliosmole of amino acids. It's like one apple is 1 fruit. So that's going to allow us to add these together. Here's creatine and lactate, the amount of ATP inside the cell, the amount of glucose in milliosmoles per liter is listed. Protein, so this is the number of milliosmoles of protein, even the amount of urea that's inside the cell. So they've listed all of the major. They've listed all the major chemicals that are found inside the cell. If we add all of these up, we will get a total of 302.2 milliosmoles per liter. Can everybody see that total? 302.2. Didn't we learn that in an isotonic fluid is approximately 300 milliosmoles of solute particles per liter? And that's exactly what we've gotten. Now right below this, that number, 302.2, was adjusted. It was downscaled a little bit to 281.3. And in fact, that's actually a more accurate number. I'm not asking you to know that. It's still close enough to 300 where we're not going to worry about it. But in case you're wondering, well, what do you mean that 302.2 became 281.3? It says over here it was corrected for ionic interaction. And you might say, what do you mean ionic interaction? Well, sometimes we don't have a full 100% disassociation of ions. In other words, it's possible that we've got a lot of potassium inside the cell, and we've also got some phosphate and some other, even a little bit of chloride, and a small number of potassiums may combine with chloride or phosphate, reducing the total number of solute particles, because we may not have complete 100% disassociation. All right? Again, when you take a chemistry class, they commonly, you may have dealt with this concept of a K dissociation constant, which is telling you for any particular chemical reaction to what extent it disassociates or doesn't. So adjusting for the fact that you don't get a full 100% disassociation of everything, we have actually slightly fewer solute particles in that water inside the cell than we might have just based on adding these numbers together. All right, now, we have learned how to convert milliosmoles per liter into osmotic pressure. You'd say we did? Yes, right up here. We said that if you take the number of milliosmoles and multiply times 19.3 millimeters of mercury per milliosmole, that'll tell you the osmotic pressure. All right? So, so that's about what it is 5,790. In this case, since the actual true number of milliosmoles per liter inside the cell is a little bit less, 281.3, if you multiply 281.3 times 19.3, you'll get 5,430 millimeters of mercury. That is the osmotic pressure inside cells. Now, let's do the same thing for tissue fluid. Tissue fluid is the fluid surrounding cells, right? Just as a visual aid, here's a cell, and here's the tissue fluid surrounding it. All right? It's we know it should be isotonic, right? Let's see if it is. All right? So we know that the chemical composition of extracellular fluids is very different from that of intracellular fluid. So in the case of the first substance listed, sodium, look, there's a high amount of sodium in the tissue fluid. It was really low inside the cell. The next one, potassium, is low in the tissue fluid. It was high inside the cell. This is old stuff. It feels comfortable, right? We've been talking about that. So we see that even though the kinds of chemicals that are in the tissue fluid outside the cell is significantly different from the chemicals that are inside the cell, when we add all these up, we get a total of 301.8. That's what you get. But then adjusting, correcting for ionic interaction, because some of the sodium ions in the extra tissue fluid might combine with chloride. So where you had two solute particles, it only becomes one if they join together. That reduces that number to 281.3. You'll notice immediately that's the exact same number that was inside the cell after we corrected for ionic interaction. So since we can again convert that to osmotic pressure by multiplying times 19.3, we get the exact same osmotic pressure. So what we're saying is, when we compare the tonicity and osmotic pressure of the tissue fluid on the outside of the cell with the tonicity and osmotic pressure on the inside of the cell, they are absolutely identical. They are perfectly isotonic with one another. It's a beautiful thing. So even though the kinds of chemicals that are in the tissue fluid surrounding the cell are significantly different than the kinds of chemicals inside the cell, the total number of solute particles outside is identical to the total number of solute particles inside, and the osmotic pressures are equal, and the cell is happy because it's not going to swell up and burst, and it's not going to collapse and undergo crenation. Is everybody okay on that? At this point, you'd say, you covered all this. You told us that was isotonic. Where are you going with this? Right now, where we're going with this is now to look at blood plasma. Now, blood plasma is another extracellular fluid. We have already learned that the chemical composition of blood plasma is essentially very, very similar to that of all the other extracellular fluids, including tissue fluid, with one exception. What's the one difference in between blood plasma and the other extracellular fluids? Protein. So what we're going to see is that blood plasma has essentially all the same solute particles, all the same chemicals that tissue fluid does, plus it's got protein in addition. So in fact, as we look at the numbers, the concentration of all these chemicals, it's pretty similar. It may not be absolutely identical. It's pretty similar to tissue fluid until we get to protein. And I underlined it because tissue fluid has essentially either zero or almost zero protein in it, but blood plasma does have plasma proteins in it. So obviously, what do you think, knowing that, can you predict that therefore if we add up all the chemicals in blood plasma, it might actually end up with a higher number of solute particles than tissue fluid? And that's what we see. You'll notice that even before we correct for ionic interaction, it's a higher number than the others. And after we adjust for ionic interaction, we get 282.6. Now compare that with the number of milliosmoles per liter of tissue fluid and intracellular fluid. These were identical, absolutely perfectly identical. Can everybody see this is a little bit bigger number than this? This is 282.6. These were 281.3. Now I know you're thinking, come on, give me a break. You're talking about a difference of like 1 milliosmol? Yes, but that's going to be important. So therefore, blood plasma is actually slightly hypertonic compared to either tissue fluid or intracellular fluid. And again, what's making it a little bit more hypertonic? Plasma proteins. Now, when we convert the milliosmoles per liter to osmotic pressure, you'd say, yeah, how do you do that? You multiply 19.3 times that. You can try it. You'll get 5,453 millimeters of mercury. Now, can you see that the osmotic pressure of inside the cell and in tissue fluid outside were identical, 5,430, but blood plasma is 5,453, which is 23 millimeters of mercury higher. So its osmotic pressure is 23 millimeters of mercury higher. You'd say, how did you get 23? 5,453 minus 5,430 is 23. Let's round it off to 25. A number you can remember, because you're going to have to remember it, okay? Because it's important. Now, the fact that blood plasma has a higher osmotic pressure of about 25 millimeters of mercury compared to tissue fluid or intracellular fluid And it's higher because of what? Because of proteins in the blood. This number is called the plasma colloid osmotic pressure. That's what this pressure is called, that difference. The word colloid means protein. The proteins in the blood plasma are creating an osmotic pressure that's higher than anywhere else by about 25 millimeters of mercury. So the fact that this osmotic pressure in blood plasma is about 25 millimeters of mercury higher than it is anywhere else is due to the presence of those proteins in the blood.